So now we have a talk from Thais Pacheco, which is on the a new synthetic spectral grid for subdwarfs and the implications of that. Thank you. You can start.
Hello, everyone. Thank you for having me here. I'm Thais from Universidade de São Paulo. I'm going to talk about a grid of synthetic spectra for subdwarfs. I built some models in Non-LTE line blanketed atmosphere models. I'm going to present this paper I published with my advisors, Marcos Dias and Paula Coelho, in collaboration with Ronaldo Levenhagen. We published the Astrophysical Journal Supplement Series. And this is a new grid of detailed atmosphere model spectra for hot and moderately cool subdwarfs. And this topic has application in determination of fundamental parameters of subdwarfs in isolation and in binaries, but we also have interest for population synthesis analysis. And just to contextualize, subdwarfs are low luminosity and low mass components, which evolve from low to intermediate mass. And this is a color magnitude diagram, which is a cross-matching Gaia data release 2 with Lamos data release 5 database. And this is a figure from Lei and collaborators 2019. The subdwarfs are colored in black here, and we have a zoom in the right panel. And we have more than 2,000 hot subdwarf candidates, which is numerous stars. So we need a grid of spectra to analyze these stars, a grid of available spectra. So these stellar spectra are showing the stronger ultraviolet emission for hot stars, and talking about radiative transfer in stellar atmosphere, because these stellar spectra are computed based on a stellar atmosphere structure. The radiative transfer in the atmosphere is described basically by this second order differential equation, which we have a balance and from mean intensity and sources, and we have extinction and scattering as absorption coefficients to contribute to opacity atmosphere. And the most popular atmosphere models are built in local thermodynamic equilibrium, which is based on Saha-Boltzmann statistics equilibrium. But this approach have limitation because it consider the kinetic ion excitation and ionization temperatures are the same local temperature. It's not true. So we need to more detailed atmosphere models, like non-LTE models. In the last decades, we have improving a lot in atmosphere models, including some ions to contribute to opacity atmosphere. And as a result, we know that non-LTE models, metal line blanketing effects have a difference in align profiles seen in the ultraviolet spectra of hot white dwarfs. And also the lower non-LTE fluxes result from the overpopulation of the hydrogen well level at the depth of formation of the continuum flux, hence implying a larger Balmer continuum opacity. Now talking about a little bit about my models. I used the TELUST 205 and TELUST 208 to compute the stellar atmosphere structures. My models have surface gravity between 4.5 and 6.5, covering 8 effective temperatures between 10,000 and 55,000 Kelvin. We have 4 abundances, choosing 2 metallicities, solar and galactic halo metallicities. And I also included all these ions as explicit ions to contribute to the opacity of the atmosphere. And in total, we have 96 models. We choose the explicit ions based on ionization energy associated to each temperature of the atmosphere. And this is a table where I'm showing the ions I included to each effective temperature. So we have between 23 and 34 explicit species included in the non-LTE atmosphere models. And about the chemical abundances, we have 2 metallicities, solar and galactic halo with alpha enhancement, and each one with 2 helium abundances. Here I'm showing a figure from Ley and collaborators 2019. The colored symbols are subdwarfs observed, where they are showing the helium abundance as a function of effective temperature of each stars. And they had a linear fit for helium-rich and helium-poor abundances. So my helium-rich and helium-poor abundances for each effective temperature is based on these 2 linear fits. Now I'm going to show some results. Here we have atmosphere structure models. I'm showing the temperature as a function of mass depth. The left part is the upper atmosphere, and the right part is the inner atmosphere. I'm comparing the profile of the structure atmosphere, comparing LTE and non-LTE models for these effective temperatures, and we can see the difference is here in the upper part of the atmosphere, which is important to line formation. And here I'm showing some density shape of structure atmosphere. In the upper panel, we have the electron density, and the bottom, the mass density. And this is 10,000 Kelvin models. We can see this little oscillation here, which is due to the convection zone, the atmosphere, we included convection in this cooler model, and the hotter models have a straight shape. We also produced an Inglis-Teller diagram, which is a classical diagnostic for density, for electron density. And talking about the spectral synthesis, I use the SynSpec for 54, covering the range between 1,000 and 10,000 angstrom, including hydrogen and hydrogenic lines and quasi-molecular satellites of Lyman alpha, Lyman beta, and Age alpha. We also treated the helium triplet lines, the helium-2 lines, which is approximately hydrogenic ion by Stark and Doppler profile, and also Stark broadening table. Finally, we use the routine to include the microturbulence velocity of 10 kilometers per second, and no rotation and no instrumental full width with half maximum. Here I'm showing the normalized flux as a function of wavelength. And for spectra, the upper spectra is the hotter, 55,000 Kelvin, and the bottom is 10,000 Kelvin. So we can see differences in this spectra, in this range, where we have helium lines, which is more important for the hotter spectra, and this forest of lines in the bluer part of the cooler spectra. And showing this zoom in Continuum and Lyman, and Balmer lines. And we can see these helium lines for the hotter spectra, and the Stark broadening is more important for the cooler stars. And here the Balmer discontinuity is almost unseen in the hotter spectra, and we can see the Balmer discontinuity better in this cooler spectra. We also have a comparison with observations in optical. Here I'm showing a comparison with models of 25,000 Kelvin and 45,000 Kelvin. We have a fair agreement with observations of Lamosty spectra. And here I'm showing a comparison with observation in ultraviolet part of the spectra, and comparison to HD 4539 spectrum. And we also produced synthetic magnitudes. And here I'm showing the color diagrams for Hubble Space Telescope filters and for stronger filters. And here we can see a color, we can see a temperature dependence. And here the circles are indicating the solar abundances, and the down pointing triangles are indicating the low halo metallicity. So we can see this linear dependence of temperature here. And in this part, in this color diagram where we are showing to Balmer discontinuity, we also have a split in surface temperature, in surface gravity. The smaller points are higher gravity, and the greater points are smaller gravity. We also have this comparison between synthetic colors and slow longitudinal sky survey data. These points, these crosses are from Gaia 2020, which is the most complete observational data of subdwarfs. These colored points are the subdwarfs with the effective temperature determined. And we are comparing this color to our synthetic color. The greater points are our synthetic colors, and we can see a fair agreement with this branch, which is a branch for isolated subdwarfs. Just to summarize, I presented a grid of synthetic spectra for subdwarfs, which was computed in in non-LTE full line blanketed atmosphere models. I included hydrogen, helium, carbon, nitrogen, oxygen, neon, magnesium, aluminum, silicon, sulfur, and iron to contribute to opacity atmosphere. We covered 8 effective temperatures between 10,000 Kelvin and 65,000 Kelvin. Surface gravity between 4.5 and 6.5. 4 chemical abundances, solar and galactic halo, each one with 2 extreme scenarios for helium-rich and helium-poor abundances. And all these spectra are high resolution spectral synthesis performed from the ultraviolet to the near infrared. You can download my grid of spectra by in these 3 websites: the spectral models of stars and stellar populations, which is Paula Coelho's website, at the Vizier, and at the Spanish Virtual Observatory. And thank you very much for your attention. I can answer your questions, or you can send me an email.
Thank you very much for your talk, Thaise. Very detailed description of the grid. And do we have questions from anyone? Okay, in the meanwhile, I can ask you a question. I didn't understand whether the BCR, all these links, they contain the spectra, so the full spectra, the full grid,
Yes.
and also the pre-computed photometry, or of course anyone can recompute the photometry as they want, right?
These links contains the full spectra, so we can compute the photometry, but we also have photometry, so we can send me an email and I can send to you which we have. Thank
you. And there is a question in the chat from Matti Dorsch. he's asking whether you see noticeable differences between T-lusty 208 and 205.
There is a substantial difference because the convection treatment is updated recently by Ivan Rubini. So the convection treatment is different. We also have some difference in the UV part of the spectras. So if you are using convection, you need to use T-lusty 208.
Do we have other questions? So there is a question from Ranjan. I'm not sure if I know the surname, but what is the reason for such a large grid spacing, only 18 TF range? Is it degeneracy or something else? Also, could you try little more fine, little finer grids in log, I guess log G?
We intend to cover space parameters, square space parameters. So between 10,000 Kelvin until 65,000 Kelvin. And of course, it's important to have a thicker spacing. We are working on this, and we are also working to do a little more thinner grids in log G. But this is a starting point grid covering all the space parameter of subdwarfs.
Any more questions? Okay, if there are no more questions, I would like to thank Vedant and Thais again for their very interesting talks. I will stop recording now.